Okay, so with that question, actually, we briefly reviewed what I have told you in this morning. Now, as I told you this morning, we are going to talk about the simultaneous heat transfer mechanism. First of all, you know what I mean from heat transfer. Heat transfer means heat from one point is transferred to the other point, or one place to the other. Imagine we have two surfaces like this. So from this point temperature, in this point temperature is T1, in this surface temperature is T2. You know that for heat transfer process, we need to have a temperature difference between T1 and T2. And if the direction of the heat transfer is in this way, it means temperature T1 is higher than T2. So this is a hint you know about that. Okay, now let's see how many combination of the heat transfer we can have. Because you already know we have three modes or three types of the heat transfer: conduction, convection, and radiation. Okay, first, when we have an opaque solid, in this type of the substances, here we don't have any liquid or any gas, actually, any fluid in motion. Okay, this opaque solid which we have on its surface or even in contact with that, we don't have any uh, fluid in motion. So in this case, because it is also opaque, so the heat transfer is only by one mode, conduction. Many heat transfer problems are for this one mode heat transfer. For example, wood. Imagine you have a wood or metal or something like that. Heat transfer through that is mainly by conduction. So heat transfer is only by conduction in opaque solid. But if it is not opaque solid and it is semi-transparent, then the heat transfer in that substance or solid is by conduction plus radiation. So opaque solid only conduction, semi-transparent conduction plus radiation, because the radiation, the ray can transmit through the solid or semi-transparent solid. And yeah, so in this mode, we have, in this condition, we have one mode in transfer. If it is semi-transparent, so we have two mode heat transfer for that. And a solid may involve conduction and radiation, but not convection. You know about that because for convection, we need to have a fluid in motion. If you just go to basic or the basic definition of each one of these modes of heat transfer, you will simply understand this. Here in solid, because if we don't have any fluid, then we can have only conduction or radiation for that, but not convection. A solid may involve convection and or radiation on its surface exposed to a fluid or other surfaces. So you can see from here. This time, because we have a solid surface and a fluid, then we may have convection and or radiation. For sure. Usually we have radiation. The question is mainly about the convection. If we have solid and liquid on its surface, we need to check if the fluid is in motion or not. If it is in motion, we have convection. Otherwise, it is still conduction. So heat transfer is by conduction and possibility by radiation in a still fluid. No bulk fluid motion. This is the important notice here. And by convection and radiation in a flowing fluid. So if we have a flowing fluid, then we have convection and radiation. If it is a stationary fluid, a still fluid actually, no bulk fluid motion, we have conduction and radiation motion. Like what you can see here. And this is a fluid, as you can see here. We have radiation for that because it is transparent. So we have radiation heat transfer. We may have conduction or convection. We cannot have both of them actually. But the fluid is in motion or not in motion. If motion, convection. If not motion, conduction. And in the absence of radiation, heat transfer through a fluid is either by conduction or convection, depending on the presence of any bulk fluid motion. I think it is clear. So if we have a fluid, stationary, conduction, motion, if it is moving, have a flow, it is a convection. So you can see here, so we have this relationship actually. Convection means conduction plus fluid motion. You can understand. This is just more explanation for defining of the convection. And this one, heat transfer through a vacuum. You may know about that, the heat transfer in the heat transfer in this mode, because we have vacuum, no medium, can be only by radiation, as we discussed earlier this morning. And usually, most gases between two solid surfaces does not interfere with the radiation. In other words, if even we have the gas, not liquid, even we have gas, the gas is not effective on the radiation heat transfer amount. In other words, it cannot absorb or emit any radiation energy. So vacuum and also most of the gases, we have only radiation. And the gas is not interfere with the gas. But liquid, as also it is mentioned, are usually strong absorbers of radiation. So it depends on which type of fluid which we have in the heat transfer process. It may interfere with the radiation, or if it is liquid, interfere. If it is gas, it does not interfere with the radiation. In examples, later you will see what I mean from this. Sometimes we can ignore the fluid. Sometimes we need to calculate the radiation transfer also for the liquid. So this is the general conclusion from this explanation that, however, we have three modes of the heat transfer. Generally, we cannot have more than two types of the heat transfer. Usually, we have radiation plus conduction or radiation plus convection. I hope it is clear. Okay, almost finished the explanation about the first chapter. Now I'm going to show you two examples related to the whole chapter, not radiation actually. So in the first example, we are going to calculate heat loss from a heating duct in a basement. So in this example, we have a duct which is located in the basement of a house, and heat loss through that will be used to increase the temperature of the house actually. So let's see what is the question. A 5-meter long section of an air heating system of a house passes through an unheated space in the basement, like what you can see here. 5 meters the length, and hot air go through that. This hot air, the temperature or the thermal energy from this hot air is transferred from surface of this duct to the basement, and this is actually a heating system. The cross-section of the rectangular duct of the heating system is 20 centimeters times 25 centimeters. 20 centimeter, 25 centimeter, as it is shown here as well. Hot air enters the duct at 100 kilopascal and 60 degrees Celsius at an average velocity of 5 meters per second. So we have air here. We know how much is the velocity of the air in this duct, and we know how much is its initial temperature, how much is initial pressure. The temperature of the air in the duct drops to 54 degrees Celsius as a result of the heat loss to the cool space in the basement. As I said, this is heating system, so it is transferred from the hot air to the cooler air in the surrounding of this duct. Due to this heat transfer process, temperature of the air at the exit of this duct will be 54 degrees Celsius. So T1, temperature at entrance is 60 degrees Celsius. At the exit is 54. So 6 degrees Celsius drop the temperature of the hot air. And now we are going to determine the rate of heat loss from the air in the duct due to duct to the basement under a steady condition. This steady condition also is important word. So from this steady condition, we can understand that during this heat transfer process, temperature here will remain 60 degrees Celsius. Temperature here remains 54 degrees Celsius. Uh, Velocity doesn't change, it will remain 5 meters per second. It's called a steady condition. Nothing change with time. It is important because if we don't have a steady condition, we need to calculate for each condition. But if we have a steady condition, our calculation would be much easier. So the first thing is rate of heat loss. We need to calculate that from air to start.
Sir,
Yes.
my friend want to join the class.
So,
Yeah, we're waiting for you for accepting the request.
okay. If you join late, it should be like this. Okay. Anyone join the class? Anyone else want to join? Anyone? Any of your friends?
No, sir.
Okay, so we have a duct, hot air inside the duct, cool air around the duct. We have to transfer from this hot air to the first part of the question. The second part, we need to determine the cost of this heat loss per hour. How much will it cost for us this heat loss to surround? If the house is heated by a natural gas furnace that has an efficiency of 80%, and the cost of natural gas in the heat in that area is $1.60 per term, which term is one term is equal to 105,500 kilojoule. So we need first to calculate Q dot loss. Each type of heat transfer we have here. Okay, to have a better, vision about any example, any problem in heat transfer, because heat transfer is only occurs by those three different modes or ways which I have already told you: conduction, convection, and radiation. So before you solve any problem, you need to determine which type of heat transfer which we have, first of all. And also you need to know if the question is about the type of the heat transfer. The heat transfer which we have here is convection and also conduction. But the good thing here is it is not question how much is heat transferred by conduction or convection or even radiation. The question is how much is total heat loss or total heat transfer. In that case, we always use this equation. Q dot is equal to m dot Cp delta T. Why we use this equation? The pressure is given, and during this process, pressure doesn't change with time. And if you remember, for a steady flow examples for control volume, we need to use this equation to calculate the heat transfer. So Q dot equal to m dot Cp delta T. M dot is mass flow rate. Cp is the specific heat at constant pressure for air, and delta T is the temperature difference between those 2 points which we are going to calculate the transfer for that. Okay, let's go one by one. Before you find the values for m dot, Cp, or even delta T, you need to have your assumptions. The assumption number one is a steady operating condition exists. How we know that is mentioned. Two, air can be treated as an ideal gas with constant properties at room temperature. This is our assumption. Why we need this assumption later we will see. To use this equation, we need to have Cp, or constant, the specific heat at constant pressure for air. How, but Cp for the air, how you can find it? You know, we have table like this. I will show you the book as well, all of these tables. Like the table which we have in thermodynamics, we have here tables as well. You can see here properties of air at 1 atmosphere pressure, or the which is the common pressure which we have at the surface of the earth. For different temperature, we have different properties for air. You can see here, for example, we have different densities, we have different specific heat, we have different thermal conductivity, and so on for air at different temperatures. So specific heat here, Cp, depends on the temperature. But for which one of these temperatures? We have two temperatures here, 60 and 54. If you remember, Cp is for the average temperature. So first we need to calculate the average temperature. We have 54, and 60. So the average of these two, 54 plus 60 divided by 2 would be 57 degrees Celsius. So the temperature is 57 degrees Celsius. How much is the specific heat? Okay, let's find the 57. 57 is between these two, 50 and 60. Okay, let's see how much is the specific heat. If you notice here, 50 is 1007 joule per kilogram Kelvin, and for 60 also is 1007 joule per kilogram Kelvin. You know, so for in this range, even you can see from this temperature 15 until this temperature 70, the specific heat doesn't change for air. But in some cases, if we want to be more specific, if it change, for this temperature, 300, 350, you can see they are different. Then you need to do interpolation. For high temperatures, you may need to do interpolation to find for that specific temperature, the specific point for that temperature. But here, the temperature which we have is between these two, 50 and 60. For both of them, it is 1007. So any number between them also will be 1007 joule per kilogram Kelvin. If we convert it to kilojoule per kilogram Kelvin, simply it will be 1.0007 kilojoule per kilogram Kelvin. So this is Cp, which this is Cp, which we are going to use in this equation. Okay, next is m dot. Do we have m dot here? What we have here is velocity of the air in the duct and the cross section of the duct. So by this information, actually, we can calculate m dot. How? By the second assumption, air can be treated as an ideal gas with constant properties at room temperature. So it means we can use the ideal gas law. If you remember, we had this equation in previous slides. I already showed you. We have rho equal to P divided by RT. Rho is the density of the air. P is the pressure of the air, which is 100 kilopascal. R is gas constant, which is in this table, for air, R, gas constant. This is table A1, I think. The air, the substance is air, gas constant is this much, 0.287. So we have R here as well. And T is the temperature. But which one of these T we are going to use? This T. Why? Because the pressure also is clearly given for this pressure. So if we substitute in this equation, we can calculate density, which is 1.046 kilogram per meter cubed. And also notice here the temperature should be converted to Kelvin. 60 plus 273. So we have density. If we have density, then we can go for calculation of the mass flow rate. But before that, we need to calculate the cross-section area, or AC, the area which is normal to the direction of the fluid flow, which means this, this area actually, which is equal to 0.2 times 0.25 meter. We have converted from centimeter to meter. Then AC, or cross-section area, which is normal to the direction of the fluid flow, will be equal to 0.05 meter cubed. So we have AC as well. To calculate M dot, or mass flow rate, we need to use this equation. M dot equals rho times V is the velocity of the fluid, AC is the cross-section density we have calculated here. If we put all of this information in this equation, we can calculate M dot. And M dot finally will be 0.2615 kilogram per second. So this is mass flow rate. We have also calculated mass flow rate. Now simply we have M dot, we have Cp, and we have the T1 and T2 as our temperature, two temperatures. If we substitute in the main equation, we can calculate Q dot loss, or the rate of heat transfer in this heat transfer process, which will be equal to 1.58 kilojoules per second. So this is the answer for the part one of the question. We have calculated the rate of heat loss from this duct to the surrounding. So this duct actually is in the basement, and we don't want actually this duct have this heat transfer. We need to insulate this duct, and this duct just transfer the hot air. Okay, so this is heat loss. This has increased our cost of the heating of our house. This duct is in the basement. So this extra cost, which is due to the heat loss from the duct, can be calculated by the other information which is given. So in each second, 1.58 kilojoule energy is lost during these, during transferring hot air to the house. This amount of this rate of heat transfer also is equal to 5,688 kilojoule per hour. You need to convert kilojoule per second to the kilojoule per hour. Simply, you know that each hour is 86 86,400, if I'm not mistaken, second. So you need to convert kilojoule per second to kilojoule per hour. So now we have kilojoule per hour amount of the rate of heat loss. Why we need this? Because if you notice here, the price is defined based on term. Term is defined based on kilojoule. So cost of heat loss during this heat transfer process is equal to rate of heat loss, this one, times unit cost of energy input, how much cost the energy which comes from the furnace, divided by furnace efficiency. This is the equation which we use to calculate the cost of heat loss in this example. Okay, rate of heat loss is this much, we have already calculated. How much is the cost? It is given $1.6 dollar per term. And you know each term is 105,500 kilojoule. One term is this much. So we use this unity conversion ratio to convert the unit from kilojoule per hour to term per kilojoule. Finally, the furnace efficiency also should be, we should put in our equation. The furnace efficiency is given. How much is it? 80%. So we put here just 0.8 because it is also mentioned the efficiency is 80%. In other words, 80 by 100. So it means it is 0.8. 0.8. If we substitute all of this information in this equation and do the calculation, finally, the cost of heat loss from this duct in the basement is $0.108 per hour. So each hour we have about 0.1 or 10 cents loss of money actually due to not well installation of these ducts. And it is mentioned as well here, 10.8 cents per hour we are using during this due to this heat loss from this duct. And it is mentioned also some more explanation. For example, for 2,000 hours, the cost for due to this heat loss from the duct will be $216, which if we just insulate the duct with some materials, we can reduce the heat loss from this duct and we can reduce the cost of heating of the house. Okay, class, do you have any question about this example? Class? Any question related to this example? Any part of that is not clear for you? This is exactly similar to the question which you may get in the quizzes or even in the midterm or final. Any question, any comment?
So far, no, sir.
Okay, I hope it is clear. If not, after this also you can contact me to discuss about that. You know, some equations are not general. For example, this one, it is based on our information which we have here. But some equation like this one, Q dot and that Cp delta T, or this one, or this one, or even this one are some familiar equation which we have in the lecture. About this table, I told you, very important table, table A15, properties of air at 1 atmosphere pressure. We use this table in most of the examples. The reason is usually in most of the examples, the medium or the substance for heat transfer is air. The cooling, if you notice, for example, for air conditioning, for the fan, for the many applications, the air is the medium for the heat transfer. Okay, the other example is about the electric heating of a house at high elevation. So you know that in high elevation, the temperature is lower. So we need to use energy to increase the pressure of the houses in those areas. So consider a house that has a floor space of 200 meter square. So the size is given, and an average height of the 3 meter at 1,500 meter elevation, where the standard atmospheric pressure is 84.6 kilopascal. This information is shown here. The house and the pressure here is given. Initially, the house is at a uniform temperature of 10 degrees Celsius. High elevation, low temperature. Temperature is 10 degrees Celsius, which is cold for us. So now the electric heater is turned on, and the heater runs until the air temperature in the house rises to average value of 20 degrees Celsius. The temperature which suits for us, or we are comfortable in that temperature, 20 degrees Celsius. Now we are going to determine the amount of energy transferred to the air, assuming A, the house is airtight and thus no air escape during heating process. It means, we don't have any leakage from the windows, from the doors, or any part of that. And air, the volume of the air inside the house remain constant during this heat transfer process. We have increasing the temperature of the air inside the house due to the heat transfer between the heater and house, the air inside the house. So if the volume doesn't change, it means this heat transfer process in part A is a constant volume process. In part B, we assume that some air escapes through the cracks as heated air in the house expands and at constant pressure. So in part B, we assume that we have leakage of the air due to, when the temperature of the air is increased, it expands and the volume tries to change actually. And if we close that, if we don't have any leakage, pressure will increase. So in part A, it is constant volume because it is tight. In part B, it is a constant pressure process. Why? Because we have leakage of the air and pressure remain. Are interested to also determine the cost of this heat for each case if the cost of electricity in that area is $0.075 per kilowatt hour. Okay, let's go first calculate solve the part E of this equation, which is constant volume heat transfer process actually. The assumptions are air can be treated as an ideal gas with constant properties. Usually in the room temperature environment or the normal temperature, which we have 10, 20, we can say these assumptions. Part B, the assumption number 2, heat loss from the house during heating is negligible. Because as you know, if we use heater to increase the temperature of the air inside the house, some of the temperature also will transfer to the wall and the roof of the house, and it will transfer to the surrounding. We assume we don't have that, and all of the heat transfer is between the heater and the air inside the house. Part 3, the assumption number 3, the volume occupied by the furniture and other things is negligible. This assumption is useful also because, whole capacity of the house or inside the house is not air. We have furniture, chairs, and many things, and their heat transfer will be different. And the volume of the house actually, volume of the air inside the house is not equal to the volume of the house. But with this assumption, we can neglect the presence of those furniture. It will reduce the accuracy of our calculation, but it is good assumption because make increase the simplicity of our calculation. Okay, first let's see what are the properties which we have here. First, we need to calculate a specific heat. Here, as again, we are not interested about the mode of heat transfer. We are just going to calculate the amount of heat transfer. Okay, so the similar equation which we had, mCp delta T or mCv delta T can be used, but here in part A, we should use this equation, mCv delta T, okay? And in part B, because it is constant pressure, we need to use this equation, mCp delta T. Okay, so you can see here, for both of them, we need to have Cv and Cp. Again, we have air. For Cp, we can refer to the table. Cp from this table, the temperature. For which temperature? For the average temperature. Temperature is 10 initially, finally is 20. The average is 15 degrees Celsius. Cp for this temperature, okay, how much is it? Again, 1.007 kilojoule per kilogram Kelvin for this temperature. And how we can find Cv? Cv, we have this equation to calculate Cv or constant volume specific heat. Cv is equal to Cp minus R. Cp we have here. How about R? R is gas constant from table A1. If you remember, I showed you before. For air, R is equal to 0.287. Okay, so we have Cp, we have R, we can calculate Cv. Cv will be equal to 0.720 kilojoule per kilogram Kelvin. So we have Cv and Cp to put in both of these equations. What are the other information which we need here to put it in this equation? How about delta T, T1 and T2? We have T1 is 10 degrees, T2 is 20 degrees Celsius. That one is also easy. How about M? M here is the mass of air. How we can calculate that? The area of the house is given and the height also is given, 3 meters. So simply we have a cube, we can calculate its volume. V is equal to floor area times the height, 200 times 3, 600 meter cubed in the volume of the house. We have, okay, now we have volume of the house, and which is based on our assumption number 3 is equal to the volume of the air. So volume of the air is 600. But what we need to put in this equation is mass. How we can find the mass of the air inside the house? By using the ideal gas law, M equal to PV divided by RT. P is the pressure, V is the volume, R is the gas constant, and T is the temperature of the gas. All of them are given. We have calculated here. P is the pressure, which is given 84.66 kilopascal. R from the table for gas at this temperature, and T or temperature of the gas here, which is 10. We need to convert it to Kelvin. 10 plus 273 will be Kelvin, the temperature, the initial temperature of the air. By this calculation, M will be equal to 648 kilograms. So now we have mass as well. Then we can put in this equation and calculate the heat loss. In part A, if you notice, we have a system here. We imagine inside the house, all inside the house is a closed system. So here we have a closed system. We don't have m dot, we have m here. So we have mcv delta t. And you know from the previous slide that in this case, if you write the energy balance, it will be actually heat balance equation for the house. E in minus E out will be equal to delta E of the system. Or in other words, if you remember, E in is for constant value is the change in the internal energy of the system, which is equal to mcv delta t. But even without this information, you need to just know that here we have a closed system. For a closed system with constant volume, we use this equation. mcv delta t. M we have calculated, mass of the air. CV we have here, we have calculated as well. And delta T, the final minus initial temperature. You know, and when you write 10 minus 20, it's okay, but the value is different. But based on your knowledge, actually, you know that here we have heat gain, not heat loss. Air in this heat transfer process is gaining internal energy or temperature. So the value is positive. This much is heat gain. 4,666 kilojoule is the heat transfer or change in the thermal energy for the air inside the house actually. And you know that it is given that the price for each kilowatt hour of the energy is $0.075 per kilowatt hour. To calculate the cost of energy in this case, we need to multiply the amount of energy times unit cost of the energy. Simple calculation. Amount of the energy we have calculated, and the amount of the unit cost of the energy also is given. But here you need to be careful with the unity conversion ratio. 1 kilowatt hour is equal to 3,600 kilojoule. Then by this unity conversion ratio, and if we put amount of energy, unit cost of the energy, we can calculate the cost of energy in this case, which is $0.097. How about part B? In part B, the only difference this time is we have constant pressure process. This time, enthalpy of the system is changed. And you know that from previous session that it will be equal to mcp delta T. We have mp already calculated, 648 kilogram. We have cp, we have those two temperatures, and this time amount is 6,525. If you notice in these two equations, the only difference is a specific heat. The first time, the first part A, constant volume, part B, constant pressure. But you can see the heat transfer amount is different. Almost 2,000 something is difference between the amount of the heat transfer in part A and in part B. So in part B, actually, due to leakage, we have more heat transfer. So this time again, to calculate cost of the energy, the unit cost is constant. We need to multiply amount of the energy times unit cost of the energy. Similar calculation. This time the value will be higher than the previous one, which is $0.136. And you can see here in this case the amount of the heat loss or amount of the energy which is transferred to the air or is required to transfer to the air to increase the temperature of the air from 10 to 20 degrees Celsius is increased. This is due to the including those leakage from the door and window parts actually. And which one is more realistic? This one, because usually we have leakage of the air from the doors and windows. And the more realistic value of the cost of the energy is this one. And because of this, usually in our calculation, we use this equation in real world to calculate the required energy for a house. We use MCP delta T. Okay, by this we reach end of this lecture. You have any question?
So,
Yes?
is it compulsory to write this long discussion in exam?
This part?
Ah,
If it is in the question, yeah. Sometimes the question is analyzing. Okay, so you need to write something like this discussion. What it means. Okay, it means for us, for me as evaluator, can understand or can see that you have understood the question. Okay, if you cannot understand the question, you cannot write this discussion. Even if you write this calculation, if you do not understand, if you have not understood the question, you cannot write the discussion. So it depends on the question instruction.
okay, sir. Thank you.
But assumption you need to write. These assumptions are important. Sometimes I am lenient, or maybe the other lecturer also are lenient and ignore this. If you haven't written this assumption, you may receive the mark. But from now, I am telling to you, please write assumption. It is important. Without, you can see here, the volume occupied by the furniture and other things is negligible. Without these, we don't have only air inside the house. Okay, because the example which we have here, and also the question which you will have for the midterm and final exam, or even for the quiz, are similar, then you don't need to be so innovative or creative to write the assumption by yourself. Usually they are just repetition. They repeat in each example. For example, air is the ideal gas. If you have this assumption, then you can use this equation. Without this assumption, you cannot use this equation. Okay, any other comment, any question? I hope these two examples are clear for you. Okay, question, comment? I heard something. Okay, class. Thank you so much. I'm not going to take your time more than this. If you have any question, please let me know. If you don't have question or comment, you can leave the class. It is almost 4 p.m. and I wish you a very good weekend and a good time.
Thank you, sir.
Thank you, sir.
Thank you, sir.
Okay.
Thank you, sir.
Thank you, sir.